Hey there, Science 8. So this is another video on optical systems. So we'll talk a little bit about refraction and the law of refraction here. So basically, the law of refraction, states that when light travels from one medium to a denser medium, the light will be bent toward the normal, and when it exits the denser medium into a less dense medium, it will bend away from the normal. So consider this when you're looking at the previous picture with the mirage. So we'll have denser air, denser or cooler air, and we'll have less dense, warmer air. Okay. So lenses also will refract and focus light. So a lens is just a piece of curved transparent material, usually glass or it can be plastic. So when light rays pass through it, the light is going to be refracted, causing the rays to bend. Of course, lenses are very useful in lots of different items. So some things that they're used in would be eyeglasses, microscopes, also telescopes, even just scopes that you might use on a rifle. So there's plenty of uses for optical devices, binoculars, and so on. Okay, so if we look at this lens here, it's a double concave lens. So they tend to be thinner and flatter in the middle than the edges. Okay, so when the light passes through the thicker, more curved areas, the lens will bend more than the light passing through the thinner areas. So you can see that they're bending away, causing light to spread out or diverge. So when things spread out, they diverge. Okay. If we have a double convex lens, it's going to be thicker in the middle. So of course, where it's thicker, it's going to basically spread. Okay. So in this case, instead of it spreading out, it's actually coming towards a focal point where it's going to converge. So again, double concave lenses will cause light to diverge, whereas double convex lens will cause the light to converge. Okay, so different size lenses can converge the light rays at different distances. Okay, so we take advantage of these properties when we're designing optical lenses with a certain purpose in mind. So it could be for different prescriptions of eyeglasses or different strengths of microscope lenses and so on. Okay. So often though, and you may have noticed this, light from the left portion of the object directed to the right, and the light from the top is directed towards the bottom. So that's inverted image. Overhead projectors and film projectors will do this as well. Okay. So we can also have image formation with a convex lens. Okay, so we can have light passing through on this side and coming through a focal point. We can also have our incident rays where there's a focal point and basically they'll come through and you will have your reflection here, or your light, pardon me, will pass through at these points. Okay, so that brings us to the wave model of light. So light can actually behave in two different ways. They can either behave as a particle, okay, or a photon, or it can behave in a wave-like manner. So when we consider that it's passing as a wave, the Dutch scientist Christian Huygens, may not be saying his name correctly, suggested that light actually travels in a wave and not as a stream of fast-moving particles. It was discovered later that that light has a dual nature, right? So the high parts of the wave are called the crest, okay, and the low parts are called the troughs, okay. So from crest to crest is a wavelength. So from here to here is your wavelength. Okay, and the height of the crest to the depth of the trough is your amplitude. So basically from here to here would be your amplitude. So this is your trough, that's your crest. Okay, so the frequency is the rate at which the crest and the trough move up and down. So your wavelength is basically or pardon me, your frequency, sorry, is the number of cycles in a period of time. And we usually measure that in hertz, right? So the first basic principle of light is that it's a form of energy. So when it reaches a surface, it can either be absorbed and transformed into other types of energy. It can also be reflected, okay? So we can take solar energy and convert it into electrical. We can also convert it into thermal, and we can convert it into chemical, okay? So the amount of energy a surface receives depends on the intensity of the light. So the more intense the light, the more light can be absorbed, okay? And we can vary the intensity of light using lenses, right? So radiation is the wave-like transfer of light from its source in all directions. So in Science 7, if you've done that, you would have learned about how radiation is a form of energy that can be transferred without a medium. So you can basically transfer energy without contact of any medium. So we can get radiant energy produced naturally. So it could be from the sun, it could be from the burning of candles, wood, or oil. Also bioluminescence, which you can find in fireflies and some deep sea organisms. It can also be created artificially by light producing technology. So incandescent, which would be your filament inside of a bulb. You can also get fluorescence, which you'll get in fluorescent lights. These are the ones that have the mercury vapor in them. You can also get phosphorescence, which basically you absorb light and it releases it. Chemiluminescence, basically the production of light through chemical reaction, and thermoluminescence. So basically something glows as it heats up. So different colors on the electromagnetic spectrum have different wavelengths, and these are measured in nanometers. So a nanometer is a billionth of a meter, and these are also measured at different frequencies. Okay, so as light waves from the sun travel through the Earth's atmosphere, they'll hit particles different sizes, including dust and other elements. So longer wavelengths, so the reds and oranges, tend to pass around these particles, whereas shorter wavelengths, blue and violet, will strike the particles and reflect and scatter. So at sunset, there are many more particles in the atmosphere due to various activities going on during the day. So you'll probably have more blue and violet waves reflected away. So what you're going to see are the red and orange vibrant colors we see at the sunset. So the electromagnetic spectrum, what we have right here are radio waves, which are very long, okay? And the frequencies are short, okay? So they're very long with low frequency, okay? And they also have a very long wavelength, okay? So your frequency will decrease as your wavelength increases, okay? These are also lower energy waves, okay? So as we move towards the right here, we're going to get a shift in color, but we're also going to get an increase in the frequency. So this is the, also we get the wavelength decreasing. So these are the wavelengths and the types of electromagnetic radiation that are very powerful. So once we get into ultraviolet rays, we're looking at electromagnetic rays that can cause damage to our skin and our DNA. And so, of course, you're probably familiar with X-rays and their potential to cause damage to your body. In some cases, they can cause cancer. And of course, famously, the Hulk was subjected to gamma rays, and gamma rays are going to be your most powerful rays, and they would have the highest frequency and they would have the shortest wavelength, right? So the next lesson, I'll talk a little bit about visible light in the electromagnetic spectrum. So thank you for tuning in, and if you have any questions, please get in touch with me.